In this lesson, we're going to talk about other roots, cube roots, fourth roots, this sort of thing. So, just as the square root more or less, quote, undoes the act of squaring, of course we learn that that's not exactly true, there are higher order roots that similarly undo the other powers. For example, cube roots undo the act of cubing something. So just as we can raise something to the third power, we can find what number raised to the third power would equal a certain result. So first of all, let's talk about the notation. Square root of k, radical k, denotes the square root of k. The notation for all other roots is similar. We use the same radical symbol, but for all other roots, we put a small number in front of the radical to denote the order of the root. In other words, are we taking a cube root, a fourth root, a fifth root, etc. So for a cube root, what we would do is put a little 3 in front of the radical sign, and that would denote the cube root of k. We also have to think about positive and negative, because positive and negative numbers get kind of tricky here. Remember that, first of all, with squaring, a positive squared is positive and a negative squared is also positive. Okay? So this is true for squaring. Therefore, it's true that if we have x squared equals a positive, that it has two solutions, one positive and one negative. For example, x squared equals 9. It could be plus 3 or minus 3. By contrast, x squared equals a negative has no possible solution. X squared equals negative 9. There's no real number that satisfies that equation. The positive and negative roots for cubes are a little bit different. Remember that if we cube a positive, we get a positive, but if we cube a negative, we get a negative. Therefore, x cubed equals a positive has one positive solution, and x cubed equals a negative has one negative solution. So you don't get the problem of double roots in one case and no solution in another case, as we got for squaring. With square roots, we can find the square root only of positives. Of course, we could also find the square root of 0, but we cannot take the square root of a negative. Okay, so for much the same reason, just as we can't square something and get a negative, we can't take the square root of a negative. But the rules are very different for cube roots. We can take the cube root of any number on the number line, positive, 0, or negative. So every single number on the negative line, we can raise it to the third power, and we can find the cube root of it. So for example, the cube root of 8 is 2, the cube root of 0 is 0, and the cube root of negative 8 is negative 2. So unlike the square root, the cube root can have a negative output. When we put in a negative, we get out a negative. For quick computations, it's good to have the cubes up to 10 memorized. Certainly the first 6 are very important to memorize, and really if you know all 10, it's kind of a time saver. And a couple things I'll point out. Notice that 8 cubed, of course that would be 2 to the 9th. Notice that 4 cubed, that's 2 squared cubed, so that would be 2 to the 6th. It would also be 2 to the 3rd squared, or 8 squared. And of course 8 squared is 64 also. So there are some patterns here that we can observe practicing our laws of exponents. So if we have these cubes memorized, automatically we have a bunch of cube roots memorized. And so that can be very convenient. Cube roots are relatively infrequent on the test, and higher order roots, fourth root, fifth root, sixth root, are even more rare. So these are not very likely topics, I'll warn you right now. But I'll say a few things in general about all roots. So this is true for every possible root, square root, cube root, etc., etc. We're going to talk about all the patterns here. First of all, the square root of a, the fourth root of a, the sixth root of a, etc., these are called even roots. So when we have an even number written there, it's an even root. And of course with a square root there's an implied 2, so that's an even root also. The cube root, the fifth root, the seventh root, these are called odd roots. So we're distinguishing all the even roots from all the odd roots. And the reason we're doing this is because the same positive and negative thing we've talked about with squares and cubes extends to all the evens and odds. As with square roots, we can take any even root of a positive number, which results in a positive output, but we cannot take an even root of a negative number. We try to take an even root of a negative number, it is undefined. It does not equal anything on the number line. By contrast, as with cube roots, any odd root of a positive is positive and any odd root of a negative is negative. So it follows that same plus and minus pattern. For other properties, I will use the notation with an n before the radical sign, so the nth root of a. And here I'm talking about a general root, and of course it's understood that n is an integer greater than or equal to 2. For all roots, we can take the nth root of 0 and it equals 0, and the nth root of 1 equals 1. So that is true for all values of n. All roots preserve the order of inequalities. So if we have 3 numbers in a row, as long as they're positive numbers, we take the roots of them, as long as it's the same root we're taking of each number, then they remain in that same order of inequality. For example, suppose we had to estimate the 4th root of 50. Well, we'd want to locate it between two 4th powers. Well, 2 to the 4th, we know, is 16. 3 to the 4th is 81. So, because 50 is between 16 and 81, we can take the 4th root of all of those, and we see that the 4th root of 50 would have to be a decimal somewhere between 2 and 3. So the test is not going to expect you to do anything more fancy with finding the 4th root of 50, but as long as you can figure out which two integers it's between, that is fine. We can also compare the size of different order roots. So for a number greater than 1, the higher the root, the smaller the actual number. So the nth root is a higher order root than the mth root, and the nth root is smaller. So let's think about this. Suppose we're taking different roots of 19. Well, of course, the square root of 19 has to be smaller than 19. Now, the cube root of 19 has to be even smaller because it only takes 2 of the square root. If we multiply 2 of the square roots together, we get 19. We'd have to multiply 3 of the cube roots together to get 19. And then we extend this logic. Well, the 4th root has to be even smaller because I'd have to multiply 4 of them to get 19. I'd have to multiply 5 of these or 6 of these and so forth. So it means that as we get higher and higher order roots, all of these numbers get smaller, but they're always larger than 1. Now, it must be true, even if we can't figure out what the decimals are, it absolutely must be true that the 30th root of 19 is less than the 20th root of 19. So in other words, we should be able to make that comparison even though we can't figure out the exact values of those decimals. Now, when we get into that region between 1, 0, and 1, then things get a little bit different. And you may remember things were different here. First of all, if we take a root, the roots are bigger than b, assuming that b is this fraction between 0 and 1. And the higher the order of the root, the higher it gets. So n is a higher order root. It's higher. The nth root of b is higher than the mth root of b. So suppose we're taking different roots, say, of 2/5. Well, 2/5 is less than the square root of 2/5. This is going to be less than the cube root, which is less than the 4th root, and so forth. We continue this pattern. It turns out that all these roots remain less than 1. So they get bigger and bigger and bigger, but they never get as big as 1. And this pattern continues with all higher order of roots. So even if we had to compare two very high roots, we could say, for example, we'd know that the 50th root of 2/5, That has to be greater than 2/5, but it has to be less than the 75th root of 2/5, and the 75th root of 2/5 still has to be less than 1. So we should be able to figure out where these four terms fall in an inequality, even though we can't figure out the exact decimal values of those roots. One way to summarize is we could say the higher the order of the root, the closer the result is to 1. That is, with numbers bigger than 1, taking higher order roots make it smaller and smaller, move it closer to 1. Taking roots of numbers between 0 and 1 makes it bigger, and they move up closer and closer to 1. So this is the pattern. Everything gets closer to 1. And one of the reasons for that, of course, is that we can take any root of 1 and it equals 1. These properties are rarely tested and only on the hardest quant problems on the test. So once again, this is not something you're going to see every time you sit down for the test. These are very rare problems. In summary, unlike with square roots, we can take cube roots of both positives and negatives. That's a big idea. In fact, we can take any even root of positives only, not negatives, but we can take any odd root of any number on the number line. That's also a really big idea. Any root of 1 equals 1, any root of 0 equals 0. All roots preserve the order of inequalities, assuming all the numbers are positive. And the higher the order of a root, the closer the result is to 1. So again, the numbers larger than 1, when we take roots, they get smaller, move closer to 1. When we take roots of numbers that are between 0 and 1, they get bigger and they move closer to 1.